Holography, holographic imaging is today's topic. So why I chose this? This is something like that's complementary, but it's an emerging area of our field. And however, there's a certain limit. Holographic imaging is not for tissue imaging, okay? But itself has a very much merit. So I want to go over with you because, you know, you guys all remember holography. It's very cool, right? You see something three-dimensional, a very cool thing from Star Wars. Like all you want to know is here. All right. So what are we going to do today to cover is first, we want to understand the general concept of holography and how is it different from conventional two-dimensional photography. Then we know that holography has a nice hologram. So how do we generate holography out of this hologram? So reconstruction of object field from hologram. I said field, and there's a reason why for that. And of course, initially the invention of holography was like 1950s early, and Dennis Gabor got Nobel Prize out of this, okay? And nowadays we have CCD camera, everything's digital. So instead of old updated film, we're gonna use a CCD or digital camera. So now everything is digital holographic microscopy. And we want to go to a little bit of this algorithm because you guys are all researchers and you guys will implement your own ways, methodology. So I want to go over some known extraction algorithm, how to extract the phase information. So let's see, what are the general concept? What are holography? And you guys remember, holography needs a coherent light source, like a laser, okay? Although even the sunlight, which is, we know, incoherent light, but even sunlight has a very short coherence length of several micron. So if you can align your optics very, very precisely, you can even create sunlight hologram. So first, what can we do with this? Okay, this is an example. My junior, my friend actually, who found a company, actually two companies of TomoCube, he sells this company's product with this nice exemplary cellular, subcellular shapes. You can see red blood cell, white blood cell, hepatocyte, and even there are like lipid droplets. And this has an exquisite resolution, spatial resolution. You can see it's a 3D. And all these colors are pseudo color. It's not a real color, but the color is based on innate property of the sample, which is refractive index changes. So this is something possible. I just want to give you an example. So what is holography? Holo plus graph. Holo means like as a whole, okay, or the entire, and graph is writing or drawing. So what we are talking about, holography means something we capture the entire information, especially amplitude and phase, which we call like optical field or optical wavefront. How can it be possible? Okay, so for recording, remember when we are collecting image, like your eyes are intensity detector. Your eye cannot see the phase, okay? So how are we gonna record the phase information? The answer is, yes, you can use interferometry, all right? So how? Let's say you expand your laser beam collimated, you shine collimated light beam, and somehow you have to interfere, so you have to split them by using beam splitter. So one laser light goes to object directly that we call illumination beam, but that will scatter, interact with the object and scatter containing the information of the object, and the other beam goes to the other side as a reference. And how are we gonna combine them two? Because this optical wave is a field, this field coming out of the object and the other reference, you put your camera film there. then what the camera film sees only intensity, resultant intensity from the interference of reference beam, a pure, clear, nice one, plus the scattered beam or diffracted beam from the object. So what you see here is totally unmaking sense intensity things on top of your photographic film. And that one you cannot even like decode because it's just a noisy pattern. However, it contains the information of the object. And how can we reconstruct? Because you know that reference beam has been interfered. So reconstruction is necessary later. You have this photographic hologram and you shine the reference beam exactly the same way originally it did, then the diffraction from there, in fact, it is encoded from the original object image. So the diffracted beam, or we call reconstructed wavefront, if you are looking at here, looking through this hologram, wow, what happens is that virtual image disappears to your eye. So this is somehow people define hologram as a lensless imaging. That also makes sense because you don't have a lens, but the field itself serves as the imaging, focusing on this virtual image. On the other hand, what's interesting is this virtual image looks almost like 3D because the field coming out of this is originally three-dimensional aspect. So holography is a method to record the entire light field information. What do I mean by field? Amplitude plus a phase. So this holography is a technique that enables a light field, which is generally product of light source scattered off the object, and that will be recorded like interferometrically, and later we reconstruct it when the original light field is no longer present, meaning that we are watching at virtual image. A simple example is you go to the Gwangju Biennale, you can find some holograms which look very, very interesting, okay? That's how you do. And this two-step process, simply I call it as writing and reading. You have to write to the hologram first by recording amplitude and phase information on a film, okay? But remember, you don't have specifically amplitude and phase on a film. You actually have the intensity modulation of interference pattern. That's what you have. And when you read the hologram, the hologram will be illuminated exactly the same way it was originally made as a reference beam, but now we call reconstruction beam. And then you will retrieve the hologram. So that's holography. So optical wave field is containing the amplitude and phase. And so mathematically, when we describe this, you remember when we first described electromagnetic wave, the amplitude and phase informations are there. So we use simply complex quantity, which easily describe amplitude and e to the j phase component. And that is, of course, it's a wave three-dimensionally propagating in space and time, so function of position and time. So traditional imaging results in Suhyun?
Intensity.
Exactly. And then amplitude information is recovered while, for example, your eye.
Phase.
Exactly. Phase information. So your eye, as a conventional detector, will not perceive, will not catch the phase. Okay. Why? You can ask why. You remember e to the wave, even plane wave propagation, amplitude times e to the j kx minus omega t. You know, this is a phase term, contains omega t, and you know that omega is a super fast, like 10 to the 14 hertz, which is like, let's say, almost close to 1,000,000 gigahertz, and that's impossible with our current electronics to catch up and calculate phase. That's why what you detect with your eye or your camera is mostly on average values. That's why we cannot collect the phase information. So then, okay, what are the differences between well-known photography versus this new emerging holography? Photography records intensity information only, like your eye as well, but holography imprints wave what information? It's both amplitude and phase. 정명?
Wavefront.
Exactly. So this is another way to say optical field is wavefront, which is more like geometrical term, but that geometrical term contains not only amplitude, but the phase information as well. All right, here, now let's review what the imaging is about. We originally discussed. Photography records intensity image. So let's think about our photography. So there's the incident illumination. It could be laser, it could be a room light. So that light comes in to your object and that will interact with your object. So imaging is about every point the light scattered out will somehow focus down. That's where your images are formed. Okay, so that scatters out. So these are like depiction of wavefront. And you have well-known imaging systems such as 4F system here. And then you will generate your image because they will focus down onto your screen. And so your imaging system, this S, by the way, stands for wavefront or the light field. So what you record is really magnitude square of the field that we call intensity information. So does that make sense? Okay, so now let's advance into our holography concept because holography has to record wavefront. So incident laser beam gets illuminate the sample. You mean the scattered light field is coming. We have a conventional lens system. However, for recording the phase, you do need the power of reference interference. So this reference beam now you shine, which what it means is where exactly known. The wavefront is exactly known so that the final, okay, the final interferogram, which is we call hologram, looks just like this. You just cannot understand what's going on, but that's where the information is inside. Okay, and what are we actually recording? This is conventional camera film or your CCD detector that only detects the final intensity information. What are the intensity? Intensity means the field at this point is S plus R. These are all optical field. You sum them because it's interfering, magnitude scale. This is what we call interferogram, and that's hologram because it's an interference pattern of both S source and reference, but we know reference, that's how we can extract the information of the source. That's the mathematical concept. So here, of course, important thing is the laser beam must be quasi-monochromatic, which means the reference has to be clean. That's why holography usually requires a laser, okay? And spatially mutually coherent. What this means is the reference beam should have a well-defined phase relationship between different points in space because they will be forming an image and interfering. So you do need a spatial coherence as well. And how can you get this? Usually this in incidence light or laser beam, you split to bypass and make this arc because this and this two has to be coherent relationship. Remember when we talk about optical coherence tomography, the light has to be coherent such that it can interfere each other. Okay, now let's move on. Now let's assume we've got already made this hologram. So how do we reconstruct? This is a kind of cartoon to show that, hey, this is a hologram. It contains that original dinosaur information. And you shine exactly the same as reference beam. So this is transmission hologram, and it will diffract the light from the hologram. But what that actually shows is, in fact, this is when you first record this light path. You look at your eye, it actually shows that there's a virtual dinosaur on the other side, even like three-dimensional shape. So that's how you reconstruct your holography. So reconstructing the wave front is, now let's look at it a little more analytical aspect. Your hologram is source plus reference magnitude square. And now you're illuminating exactly the same way the reference beam used to go, shine. And then now what's happening on your image plane? So, you know, the field from here is exactly over there. That's what the optical imaging is about. So what happens to the field over here is you send out the R, so R, and R is modulated by your hologram, which is intensity modulated. So this is the original. And that forms the field coming out here, and you're imaging that. Okay, so let's just solve this one. You know that this is complex quantity. As I said before, it's a field, amplitude, and phase. So this A plus B squared is S plus R times S plus R complex conjugate. Then you calculate this, and then you will have this component and S component, source, and complex conjugate. So you can rearrange with this. And let's think about what is the simplest way of sending out the reference, which is, of course, a plane wave, right? So Laxman, so plane wave, how can you describe plane wave in a phasor format? So let's also amplitude 1, then e to the j, 2 pi. Answer is not that far away though.
Mu naught.
Exactly. And what do you mean by U naught? U naught is like 2 pi kx. So it's a wave number with respect to the x-axis. So 2 pi U naught. So you just put 2 pi U naught here and there. The interesting thing is the magnitude of R. You just, it's a simple one. So it's 1. So this becomes 1, and this comes R square coming into here. So you see S square, this is 1, this becomes this, R square is 1, and this R square is this. And that's what the reconstructed field to be imaged. So this is gonna be imaged in your imaging space or imaging plane. But remember, this is a field, okay? And what is U naught? U naught is, you remember, recall U naught is X component of your wave number. So that is a 1 over lambda, but because of the angle, angular oblique angle of theta of the wave versus this reference to the optical axis, that's a theta, that angle comes in. All right. So then let's look into one by one of these the terms. Let me go back one more time. Remember this, just take a picture with your eye of that, okay? So there's a 1s component, there's S complex conjugate component, there's no S component. And this one comes here exactly the same. But now this is an optical field. Now we want to look into a little more geometric way, actually Fourier domain way, because remember that e to the 2 pi u0 contains sine theta. So that it has a sine theta angle from the original optical axis. Okay. And this is 2 pi times 2 u naught. which means twice of the wave number. So what that means in geometrically, this is a twice of the angle, because we are talking about now angular aspect. So that component is actually 1 theta, 2 theta. This component is 1 theta, and the constant has no angle, so it's going through the optical axis. And now reconstruction of the hologram means you have to shine onto your hologram. So hologram is this one, and you are shining reference, then the reference angle has to be exactly the same as the original, which has an angle theta, and then you shine, you will have these 3 diffractive light components, okay? 3 directional diffraction components are coming out from the input of R reference from the hologram. So this is a key aspect of what's coming out. And I'm gonna go through a little bit of term by term. So this S, this one is on axis, okay? Because that's what we want to know, the source. What about the other components? So that's 1 theta. So this is theta, you have this term, that's coming out. What about, let's see, not, can you guess what geometric angle is this?
I guess it's
This is 1 theta, and this is, and you see this mu naught and twice of mu naught.
twice of theta.
Exactly. Yeah, 2 theta. Okay, but this 2 theta information has not S, but S complex conjugate. So that's a little different. All right. So what we want is S, but the others are like junk. So we want to eliminate. So I put this gray color. So let's just remove this. What do I mean by removing this in real optical setup? So let's filter out that one. Then we have to consider the, okay, I think I have, okay, sorry. I want to, okay, I want to show this one first. You remember that 4F system, reference is there, hologram is here, and you shine, there's a 4F system. You know that the field's Fourier transform is at the middle of this imaging system, 2F, 2F, right? So let's watch at the Fourier plane or back aperture of the objective lens. That looks like this. From the 0 to farther and farther away, this is a theta angle correspondence, this is 2 theta angle. And we know from here, there's S is coming out. Oops. And then 1 theta, this is coming out. 2 theta, this complex conjugate coming out. In fact, when you do Fourier transform of the original, so this is Fourier plane. So this is original spectrum. So S Fourier transform. But what about this one? When you Fourier transform of this, first of all, the multiplication of this Fourier transform means you have to move this place in Fourier plane by the amount of U naught, okay? And this Fourier transform is when there's a Fourier transform of like S magnitude square or S times S complex conjugate, that will come out Fourier transform of autocorrelation of this S. Okay, so that makes this one actually twice of wider in terms of pass band. Okay, so this contains the information of what we want, but this one is not what we want, and this one contains S naught. So this is also not what we want. So this is gonna be, let me see, transform of equation 1 from the before, it's or at the Fourier, now plane information. This is a Fourier plane information. So in fact, Sadaf asked a question, why do we have to learn Fourier optics? All these ones really understanding depends on our, clear understanding of Fourier optics. So this is what I want to show. So how can you reconstruct this wavefront with reference illumination for reconstruction process? So remember, this is a Fourier plane, and we know that B and C's are not necessary. So you just make a hole for this A only. Then this hologram, you shine the reference, and then this diffraction out of this, only the A component is what you want and not the B and C, because A contains the S information. So you have 4F system at the back focal plane of this lens or Fourier plane, you just make a hole for this. By blocking the others out, then what happens? The Fourier transform of this only shows the S. The field at the image plane replicates the original S stored in your hologram. Okay, so again, this we call this process as a filtering. So filtering or of passband W. So this, spatial frequency content of W or slightly greater. This W is defined by the way the complexity of the original sample and imaging. Okay, permits the desired term A only to pass and eliminate the undesirable terms B and C. So, reconstructing holography is a trick with this, right? So now, let's move a little bit of, you are talking about hologram made out of the film, okay? That's nice, but that's old dated one, okay? So this modern world, anyway, hologram is anyway intensity based. You make interferogram as intense. So you can use typical camera for recording that. And hopefully you can also reconstruct from your camera. How can you do that? Even I want to do microscopy too. Okay, that's possible. The concept is you have a laser, you split the laser beam into two, one called sample beam, the other called reference beam. You somehow have to interfere them, and one laser light goes in through this sample. So there's imprinted laser light, the sample, and you shine a reference, and you both mix them together and put it into the image sensor. Yeah, that's the hologram. And now your hologram is within your CCD camera, and how can you extract the original sample information is the question. And I just want to show one good example of this setup. Look at this, a nice diagram over here. This looks like cartoon, but no, this is the actual data reconstruction of the monolayer of cell. But this cell looks very interesting. This cell is undergoing apoptosis. So there's a blabbing on the side, and this cell is dying. Maybe the other cells could be like immune cells who actually kills this cell, potentially, right? So that's digital holographic microscopy I want to discuss with you. So how can we make it? So-called DHM. We reconstruct the complex field at the sample plane based on image recorded by CCD, or nowadays as CMOS, scientific CMOS camera, at the hologram plane. How can you implement? As it turns out, it's not that difficult. While the implementation, this is interference technique, so you're gonna suffer from fine alignment, and vibration is very delicate. So this is the example. Looks like complicated, but let's go through a little bit. First, you have a laser light. You need the beam splitter. You have to split the beam into one reference beam. Looks like, be careful, this reference beam is a little angled here. So this is called off-axis holography. And the other beam gets into the sample, of course, interact with the sample, and you combine them. So you do need another beam splitter to combine them. So that's basic configuration. And 정면, so the inset we have a cells over here mounted a perfusion chamber. So this O must be, Jungmyo, can you guess what this O means? One is R is a reference beam wave, and O is
Optical.
not optical, but object wave, because it goes through the object or objective lens, right? And BS, Jungmyo?
Beam splitter.
Great. I'm happy that you don't say bullshit, okay? And mirror and MO is microscope objective. Okay, so now you guys all know how to build a digital holographic microscope. Okay, so now you build it. Let's take a picture. And this is the picture out of this. You know, this is very, very cool. So in fact, what you get the field at your CCD plane OXYZ, and you can propagate to sample plane when Z equals 0. And what you get is, in fact, this amplitude distribution times e to the j of phase information of XY. So because you are taking full field image, XY, there's H. The H actually means the thickness of the sample, because you assume the sample, in this case, a cell has a different refractive index compared to outside media, and that is true. So you assume that constant, and the phase difference you make it, then you can actually retrieve the H, which means the height of the cell. We call it cell profilometry, and you can actually make this nice 3D looking cellular shape, which shows like thicker into on your the cell nucleus. So does it make sense? But however, the caveat you have to ask is, we are assuming the constant refractive index of the cell here. So the height here, so you see phase information is here, but reviewers ask, what are the estimated height? So they put this distance, but this distance is not exact. You have, they are assuming constant refractive index inside the cell. That is not true, okay? So that's why they put this a little bit this weird way, because it's old paper initially. So now the question is, hey, we've got record hologram. How can we find out the original sample information? That's a question. And now you have to think it more analytically. So first, your reference beam is what? It's a plane wave typically. Plane wave contains sinusoidal wavefront phase change. So it's a ruler, and obviously you cannot get better resolution than that. But how to reconstruct the phase of the sinusoid, you do need at least 1 to 3 points. Like 4 points is better because the sinusoid ups and downs to reconstruct. And here comes the Nyquist criterion. In fact, it's the same, okay? So you do need somehow multiple measurement might be necessary to retrieve the reference beams or the phase information. So this is a nice depiction of that. So now you have a camera, you have a test surface. This is in fact Michelson-Morley's interferometer. Light source, you have a laser, light go to the surface, you go to reference mirror because you are combining them. So that's kind of hologram. In fact, this is a simple interferogram though. And you want to know the test sample exactly. So one shot, you'll have interferogram here, but you see piezo. So you can actually move the reference beam at the nanometer scale, which is sub wavelength. So you can control the reference beam's phase well enough. So in theory, you have to know the reference exactly, the detail in terms of phase. So you actually need at least 1, 2, 3 steps at minimum to recall the reference so that you can extract the test surface information. So that's the basic idea. And this we call phase stepping, or if you look at literature, phase shifting interferometry. What's great about this? You can take the whole field simultaneously. That's good. So you can have high resolution. What's bad about this? You have to move the reference mirror at least 3 or 4 times. And then you have to take that time. You have to take multiple images. So focus on that limitation of this approach. So we call phase shifting interferometer and imaging, and a typical way to 4-step method. So let's see, you shine the light, okay? And then one arm goes to sample, interact with the sample field is coming back. The other side go to the reference arm, go to the mirror, coming back. So you combine them. So that's interferogram or hologram too, right? That's what you image. So that is just simply F plus G field magnitude square, then you can actually compute this. What are the differences between these two? Are the optical path length difference, which is constant delta phi over here. And what you want to know about this sample field is amplitude times e to the j phase information, pi x comma. This is what you want to know in the end. And the reference is a simple, there's nothing, it's a plane wave. So the simple one, you put it there and you compute. Now you want to extract this one, but you have a control of only that relative phase difference of this delta phi. How can you control this? Just you put PGT phi delta phi as a 0, 90 degree, 180, 270 degree. Then you will get 4 types of final interference pattern. And from here, it's an algebra. So you can do it at home, but simply you want to retrieve phi out of this. Now you know that cosine A plus pi over 2 is minus sine, and this is minus cosine. This is plus sine. So that the phi information can be easily computed as 2 out of coming from cosine, 2 are coming from sine. So tangent is sine, cosine, sine over cosine, and you will easily compute this one. Let me see, Suhyun, can you guess what this is? You can guess from the beauty of this.
I3 minus I1.
Nice, great, good job. So everyone, later on, you should do it with your head. It's not going to be that difficult. So you know the tangent value out of this for each point, so you can find the phase information of each point. That's how you reconstruct the sample information. So it's that simple. But look at that. The problem is you have to take 4 images by moving this piezoelectric device. That will not allow a fast imaging. That's a limitation. So to resolve that, people developed a newer method called off-axis holography. On the other hand, this is called a single shot holography. That sounds awesome, right? So what do I mean by single shot? Hey, you don't have to move your reference arm 3-4 times to collect multiple interferogram and then compute. No, you don't need. How? You just send your object on, but your reference arm somehow tilt your reference arm, which is a plane wave usually. What are the tricks? When you put this one into hologram and you process it in Fourier plane, you know, optical Fourier plane means geometrically, you just Fourier transform of your image, in fact. Okay, so that is a Fourier plane. Likewise, what we did before, like O object, complex conjugate O, and O magnitude scale will come out, but not overlapping each other, but in spatially distributed. So digitally, we just take this part and throw out this part, and just this part putting back to the center, and then inverse Fourier transform. That's the trick. So what this means is, wow, that's great. You can have a single shot holography and you can retrieve your object directly. Okay, that sounds very good, very cool, wonderful. You know, everything has a trade-off. What are we missing? This is a Fourier plane information. You are taking only a piece of it and take that out. So your Fourier plane information is narrow. That means you are losing your resolution. Everything has pros and cons, right? So that you want to keep in mind. And I want to go a little bit more of a detail of analytic form. So you send the light, you have a mirror, you go to sample comes back, and the other typical reference arm comes back. Oh, wait a second. You didn't do a good job for your alignment on purpose. What happens is reference arm is now tilted. So majority of reference is plane wave, majority of sample is plane wave. What happens when two plane waves are oblique angle going shine? Look at that. You'll have a nice line sinusoidal interference pattern. That's what you are expecting. So F and G, F is what you have a sample, and you are usually interested in the phase of the sample, and G is now not a simple constant, but it has 2 pi u naught x, which contains that angular tilting angle over here, okay? So when you compute this, now you can have like sample arms in intensity, reference arms intensity, and 2AB cosine these angular difference. This is what comes out to you, okay? And now you don't need to take multiple images. You have this interference onto your interferogram, and it contains all this information. But when you Fourier transform it, or thinking about looking at an back focal plane or Fourier plane of this imaging, you can now actually extract phi directly. Right. Then you have one single shot imaging of holography. Okay, so let me go back to 4-step method again. In fact, the geometry of light goes in, beam splitter split, and then you combine, one arm goes through the sample, the other arm goes to reference. You combine this like kind of a rectangular form of interferometry we call Mach-Gender geometry, Mach-Gender interferometry. So this is what it looks like. So now you guys are all inventors of, you know, single shot for holography. Let's go through. You send a plane wave, you have a beam split into reference arm and sample arm goes through sample, in this case, red blood cell, which is better to be a little transparent. And you have send it, and the reference arm, you don't need to align very well. You need to have a tilt. Then because of tilting of this off axis or oblique angle, you will have this overlaying nice standing waves coming on top of this red blood cell. How mathematical we describe this? Because your electric field is a combination of both of the 0 and 1, and delta phi is actually sample. So this one is your reference, which is oblique angle. Because it's angle, it's not just constant, it has J. But this angle, let's consider the angle is a little two-dimensional generalized angle, like x-axis, y-axis, theta and phi. So that's u naught x plus v naught y. This each of these contains 2 pi over like sine theta and sine phi. And then you just magnitude square of this. You do it mathematically, then you will get the first term magnitude, second term magnitude square, 2ab, and times this one as a cosine the phase differences. So what do you get on your CCD camera is really I is constant plus original oblique angle plus twice of original. Actually, this is go back to twice, this is minus, okay? So E0 is reference and E1 is through the sample. And that intensity now you can digitally process in your Fourier domain and then reconstruct that delta phi xy, the phase distribution. So that's the key. How? This one I just rewrite, okay? If you look at this one closely, simplified way, this is constant, and this one is in Fourier domain, this is a shift by U0 and V0, and the other is minus direction shift, minus U0, minus V0. Okay, then what you can do is you just Fourier transform of this. So FFT of this one will give out capital B plus C, but Fourier transform of one function times e to the j U0 x actually means you have U minus U0. So in Fourier domain, it's a displacement. Like this one is minus minus plus, but what you want is actually C, this term, not the other term, not the C naught term. So this is the original interferogram, hologram. This is the intensity Fourier transform, and you can see 1, 2, 3 dots, okay? And here what you want is actually this one, not that contains the phase information of your interest. So you remove this one digitally, just bring this one back to the center and inverse Fourier transform. Boom, what you get is a nice RBC phase distribution here. So hopefully this one gives you a good idea of how digital holographic microscope works. All right, so let me give you a summary. I discussed about concept of holography, the whole entire field writing, and then reconstructing that a field which is impossible to collect conventional imaging intensity method. So we discussed about even not analog, but digital holography. And I discussed about 2 ways. One is phase stepping method to reconstruct. Keep the resolution high, but it takes time because you need a multiple phase shifting and take. The other cool way is off-axis holography. You just take one single shot hologram at the cost of lowering your resolution, but it can be real time. It's a super fast because single shot only limited by your camera speed. And the bottom one, I just added right before the class. Hey, I want to share what my invention. So this has been patented in Korea and US recently, like 2019. I worked with a Professor Won-Sik Choi, and we invented an idea of this hologram into a tiny endoscope that this endoscope can have 1 millimeter diameter, but still can result by having this 2-arm and beam splitter. This is based on off-axis holography. So I just want to share that, hey, you can just think of this and you can invent something. Cool, all right? And this reading, the first inventor who's got Nobel Prize out of this holography, and this is a more recent review.